I'm going to begin this lesson by just going over the last part B of 27.4 because I think we ran out of time a little bit on the last lecture. I just want to make sure that you understand. Okay, so we're looking at the cutoff wavelength. On our graph, we plotted the cutoff frequency. Okay, and remember that the work function is the minimum energy required to just get those electrons moving. Okay, so in order to solve this problem or get this equation, we do it by setting the kinetic energy, which would be the kinetic energy of the electrons flying off, to 0. So therefore, the energy of the photon would be directly equivalent to the energy of the electron required to get that electron to jump off that metal, which is the work function. So HF equals the work function. Okay, and again, we're asked wavelength and not frequency, so we just have to use our wave equation to relate wavelength or frequency to wavelength by including the speed of light. So if we just do a little algebra, we get that the minimum wavelength or the cutoff wavelength would be h times c over the work function. Okay, now just a note, anytime that you are using C or meters per second, you need to have Planck's constant in joules. Okay, so that's how we are, converting back and forth between, or why we're converting back and forth between electron volts and joules. So here you have Planck's constant in joules times the speed of light divided by the work function in joules. So that conversion was made up above. And so you get the minimum wavelength to be 505 nanometers. Okay, so hopefully that clears that up. Right? So we're going to talk about X-rays today and sort of make some conclusions about waves, or light as both a wave and a particle. Okay, so we saw through the photoelectric effect that electrons or photons can bounce off of a material and can cause electrons to jump off. Okay, so electrons absorb the energy from a photon. So the question is, can an electron then emit a photon? And the answer is yes. That's what an X-ray is. And we actually did first X-rays like in the late 1800s, but we really didn't know what we were doing. So over here, if we look, this is the setup for a simple X-ray apparatus, okay? So you have a really high voltage source. So the extremely high voltage source is essentially going to cause electrons to fly across this tube really fast, right? Because you've created a huge potential difference. And so as they fly really fast past this, or through this tube, they're then going to strike the tungsten target. So they hit this metal and stop. So if they're carrying a huge amount of kinetic energy and then they all of a sudden stop, conservation of energy, that energy has to go somewhere. And so what actually happens is it comes off in the form of a X-ray photon. Okay, so let's kind of look at how we can do the math here. So remember that work is equal to QV, or electrical energy is equal to QV. And over here you can see that we say EV because we know we're dealing with an electron. So the charge of an electron times the potential difference over here is what is going to give us the energy. Okay. Now, as the electron strikes the surface, it is then going to create an X-ray photon that has the energy equivalent to the energy of the electron. It's conservation of energy, completely conserved. Okay, and from Planck's equation, we have that energy of the photon ejected must be equal to HF. So right down here, all we do is we have that equation. We set the energy of the electron, E times V, equal to the energy of the photon, which would be HF max. And that would be the maximum, assuming that energy is not lost. Okay. Now, a lot of times we want to know wavelength instead of frequency. So again, we see here that we have, subbed in for C over the wavelength, and it says wavelength minimum because we know that frequency and wavelength have an inverse relationship. Okay, so let's just look at an example. So it says calculate the minimum wavelength produced when electrons are accelerated through a potential difference of 100,000 volts, which is typically what an X-ray is. Okay, so here we just have solved for the wavelength, and if we look back up at the equation, okay, essentially all that we've done is we've multiplied by the wavelength over here and then divided by EV. So you get HC over EV equals the wavelength. And then we just plug in our information. We have H, again in joules, because we're going to be using a velocity, the speed of light, divided by the charge of an electron times the voltage, the potential difference, which is 100,000, okay? And so we get the wavelength of the photon that is emitted being 1.24 times 10 to the negative 11th meters, okay? So based on these experiments, we should start to realize, and experiments from the last unit, we start to realize that wave is both, or that light is both a wave and a particle. It behaves, it can have wave-like properties, it can have particle-like properties. And this is what led to the idea of wave-particle duality, okay? Now, if we look at the electromagnetic spectrum, so these are all electromagnetic waves, and they have different names based on their wavelength or frequency. At this end, these have really large wavelengths and low frequency, okay? So TV waves, radio waves. Physicists who study this end of the electromagnetic spectrum typically look at light only as a wave, treat it only as a wave. They're concerned with, you know, diffraction and refraction of radio waves, TV waves, okay? And that is because, for the most part, that light at that end of the spectrum behaves like a wave, okay? Now at this end of the spectrum, at the smallest end of the spectrum, where we have very tiny wavelengths and really high frequency, and the wavelengths are, you know, about the size of an atom, okay? They have those light waves typically act like particles. So physicists who study that end of the spectrum look at light mainly as a particle. Where we started to discover the wave-particle duality, it was in our observations in the center, which is where it is easiest to see, you know, particle like light acting like a wave, or wave like light acting like a particle, okay? So it makes sense that, you know, our experiments that allowed us to first discover this duality were right in this range. So that visible light we saw as a wave, okay? But when we first started looking at UV and X-ray sized light, that is when we started to discover all these particle-like properties. Okay, so deBroglie in the 1920s had the idea that if light, which we thought was mainly a wave, also had particle properties, okay, why can't mass particles that we, you know, usually think of as a particle, like an electron or a proton, behave as waves, okay? So his question essentially was, does an electron have a wavelength? And after some experimentation, actually by these two guys called Davidson and Germer, they actually proved his theory that yes, particles that have mass, like electrons, as opposed to photons, which we were talking about before, also have a wavelength, okay? And it's called the deBroglie wavelength, okay? So when we talked about Einstein, he reasoned that photons had mass, or that photons had momentum, okay, but they didn't have mass. So we related their momentum to their wavelength in that P equaled h over y. Okay, so this is where deBroglie's equation comes from. It is relating, it's kind of working backwards. It's relating the momentum of an object that had mass to the Planck's constant over the wavelength, therefore solving for a wavelength for that object. Now, the experiment to prove that mass particles had a wavelength was done on electrons because they're so small, it's easier to observe their wave-like properties. They're closer down towards that electromagnetic spectrum. Okay, but all particles with mass have wavelengths. So let's take a quick look at some example problems using deBroglie's equation, which is for mass particles. Okay, so the top example is looking at the wavelength of an electron. Okay, so this is experimentation that was done, and we actually, saw, and it was measurable. Okay, so here's the mass of an electron. Let's say the electron is moving at 1 times 10 to the 7th meters per second. So if we wanted to solve for the de Broglie wavelength, we just use Planck constant divided by mv. Okay, now again, we have v velocity, so we need to be using the Planck's constant for joules. And so we get the de Broglie wavelength for an electron to be 7.28 times 10 to the negative 11th meters. We can also then calculate the de Broglie wavelength for large particles. Okay, so like a baseball that has a mass of 0.145 kilograms and is thrown with a speed of 40 meters per second. We use the same equation, plug in the information here, and we get a de Broglie wavelength that is 1.14 times 10 to the negative 34th meters. Okay? Now, it's obvious, and we should know, that this wavelength is relatively a lot larger than the wavelength of a baseball. The smaller that the wavelength gets, the less likely we are to see its wave-like properties, because all of the wave-like properties are observed. For like a good example is the diffraction experiment. We shine light through a diffraction grating that had slits that were very, very tiny, and the wavelength could fit in between the slits. So and we were able to diffract and bend that light around, okay? But it's not reasonable that we could have a baseball that would be able to fit through something that was smaller than an atom. And that's why we don't observe the wave-like properties of large-scale objects, although they do have it. So in the next lesson, we're going to be talking about Compton scattering, and that is what Einstein used to prove that photons had momentum. So stay tuned.